Hello, thank you for watching this video. So in this video, we'll be doing proportionality. So it's a proportionality prediction. I have someone here who's attending our session and we'll work on it and see how it goes. So to get to proportionality, there are a few things that I want to mention first because we are heading towards the proportionality theorem. So I want to define a few things and explain a few concepts so that when we get to proportionality, we're all on the same page. So the first thing that I'm going to talk about, I'll talk about ratios, right? I'm sure you've heard ratios so many times, but you don't know what they actually mean. You know how to find a ratio of something, maybe, but you don't know what it really means. So, or what is the point of ratios? So, I'll say that ratios are used to compare two numbers, right? So, how much one number, or actually not numbers, but quantities of some whatever can be physical quantities, can be whatever. So ratios are a way of comparing numbers. That is the simplest that I can define it. You can say this number is half the other number, or this one is double the other, all those kind of things. Those are ratios, but maybe worded more clearly than a mathematical way of writing them. So if you think about it, let's say a ratio is a way of comparing numbers. So I'll define that and say ratio is a way of comparing numbers. So in that way, you're saying how much is A compared to B. I'm not sure if that makes sense. You can say B is 5 times bigger than A, or whatever the case might be. So those are ratios. So I'm going to do a few examples of ratios and then see if we can see or maybe understand what they actually mean. So the first one, let's say we have a school, right? We have a school here. So on this school, we have 100 learners, right? And out of these 100 learners, 25 are boys, and the remaining 75 are girls. So now let's suppose that I'm asking you now, what is the ratio of boys to girls? I'm not sure if you get that. I'm asking you, what is the ratio of boys to girls? So that is very important. The order is important. I'm asking the ratio of boys to girls, not the ratio of girls to boys. So the order matters. Which one are you asking relative to the other? So what I'm asking here, so I'm saying calculate the ratio of boys to girls. So the order is important. You start with the boys and you start with the girls. So if you're looking for the ratio, it must be following such an order, right? And now we're saying it's a way of comparing numbers. The sign, the mathematical sign or the mathematical operation that we use to compare numbers is the division. So you can think of divide as some sort of comparison, as a way of comparing. So here's a calculator. I'll get this one. So you can think of divide as that comparison, right? So if you want to find the ratio of boys to girls, what are you going to say? You're going to say, okay, we want all ratio of boys to girls, right? So it's going to be what? It's going to be the number of boys, which is the one that you want the ratio of boys to that of girls. So you are comparing boys to girls. So it's going to be the number of boys compared to the number of girls. That's it. In that case, you're going to, how many boys do you have? You have 25. How many girls do you have? You have 75. So what is the ratio between the two? Ratio will come out to be 1/3. Are you happy with that?
Yes.
So this is one way of writing ratios, as a fraction, right? Another way, you can write them as two numbers separated by a colon. So in that case, this same ratio is the same as 1:3. I'm not sure if that makes sense. So we said this is a number of boys, and that is, so this is the ratio. So which is This is one. This one represents some sort of boys, and this 3 represents some sort of girls. In a similar way, when you see this ratio here, this should be representing whatever came first. Should represent the boys, and that is representing the girls. So, what does this ratio actually mean? If you're looking at this ratio, it says, for every boy, there will be 3 girls. I'm not sure if you get what I'm trying to say. For every boy there is in that school, there will be 3 as much number of girls. For example, if you have 2 boys, you should be having 6 girls. I'm not sure if that makes sense. If you have 5 boys, you should be having 15 girls. So, whatever the number of boys you have, for girls you will have 3 as much, or 3 times over. So, if you think about it now, if we want to say we have 25 boys, which we should have 3 times the amount for girls, which is there will be 75 of them. That's what ratios mean. So you're comparing numbers. You're saying for this group, there will be this much for the other group. Does that make sense?
Yes.
Okay. So let me pull another example. Let's say you have let's say this was example 1, right? I'm going to go to example number 2. Are you happy with this? So let's say now you have a bowl, right? And this bowl of you have grapes here. These are grapes inside your bowl. There's a lot of them. So in this bowl, you have how much? On this bowl, you have the numbers. Okay, let me check the numbers and see if I can get the proper numbers so that we're not sure. For this bowl, you have green grapes, right?
Yes.
Grapes, you know these ones, right?
Yeah.
Let's say you have pinkish red grapes. Let's say now you want, you are told that for the green grapes there's 88 of them, right? And for the pinkish red grapes there is 132 grapes, right? Now, let's say you are asked now to find the ratio of the green grapes, or maybe let's say the ratio of the pinkish red grapes to that of the green grapes. So what do you want? They are saying calculate. I said they say calculate. Calculate the ratio of what? Of the pinkish red grapes to what? To green. Remember, I said the order matters here. Not sure if that makes sense. So if you want the ratio of the pinkish red grapes to the green ones, so it will be the number of red ones, pinkish red ones, divided by the green ones. I'm not sure if that makes sense. So in that case, to find our ratio, it's okay. It will be a number of what? Of pinkish red grapes over the number of green grapes, which means it will be your 132 divided by 88. What is the answer to this? 3 over 2. Which means this is your ratio in a fraction form. So you can also write it in a more common column form. So it will be 3 is to 2. Which means in that bowl, for every 3 pinkish red grapes, there will be 2 of them. There will be 2 green grapes. This is what this means. I'm not sure if this makes sense.
It
Does it?
Yes.
Okay. Let's do the last example. So example number 3. Let's say you have this box over here. Let's say you have this box here. Can you see it? Okay. So this box over here. So let's say this box of yours have a length of 22 centimeters. This is your length, right?
Yes.
And your breadth, 44 centimeters. And your height, which is 88 centimeters. I'm not sure if that makes sense. So let's say now you are asked to find the ratio of the length to that of the breadth. So that's it. Calculate 1. Calculate the ratio of your length to that of the breadth. So this is your length, this is your breadth. So in that case, you say, okay, easy. It will be my length over my breadth. Does it make sense?
Yes.
So it will be 22 centimeters over 44 centimeters, which is equal to a half. Are you happy with that?
Yes.
Let's say you were to asked to find now the ratio of your breadth to that of your height. Length of your breadth to your height. So you say, okay, my breadth to my height is equal to 44 over 88. What is that? It's also a half. Are you happy with that?
Yes.
So these two ratios of yours are equal. Are you happy with that?
Yes.
So I'm introducing this because I want to define or maybe define some word that will include proportionality or proportional. So we say that two ratios are in proportion or proportional if they're equal in order, in size. I'm not sure if you get that. So by saying proportional or by saying in proportion, I'm saying the two ratios in question are equal, which is the two ratios that are involved will be equal in measure. I'm not sure if you understand what I'm trying to say.
Yes.
So in this case, this is half and this is half. So these two ratios are in proportion. I'm not sure if that makes sense. And one can say these two ratios are proportional. Now, in this case, because I'm saying these two ratios are proportional, we're saying now we have the length over breadth equaling a half, and our breadth over our height also equals that same half. Now the question becomes, if you have two ratios that are proportional, does it necessarily mean, look, in this case, we have both this ratio equal to half and this ratio equal to half. Does it mean the length is equal to the breadth or the breadth equal to the height? Not in general. No. Because in this case, if you're looking at this, you will say, okay, what I was asking actually, I was saying that because this ratio is equal to this and this ratio is equal to this, does it mean your length is equal to 1? Does it mean your breadth is equal to 2? No. It's not. Because look, your length was 22 and your breadth was what? Was 44. So, definitely not. Same thing. Having this ratio does not necessarily mean that this will be 1 and here should be 2. Because it doesn't make sense. No, it does. We can see that it does not work like that. Because we have our length over there to be 22 centimeters. And our breadth was 44. And our breadth was 44. And our height was 88 over there. So, having two ratios that are equal in measure does not necessarily mean having two ratios that are equal in measure doesn't necessarily mean that the ratio that you see over there represent the actual values of whatever the parameters that were measured. So it's always safe to think of the number that you see there as a simplified version of the real number. So I didn't say just because now we're being specific here because we have 1 over 2. So next time you might see other ratio equal to 1 over 2. It does not necessarily mean whatever the numerator was is that value there and the denominator was that value there. So always, it's always safer to say that, to think that whatever number that you see there is a simplified version of whatever the numerical value was there. It is safer, in my opinion. I'm not sure if that does make sense.
Yes, it does.
Okay, so you need to keep that in mind. So the value the ratio that you see there, always think of it, or it's safer to think of it as a simplified version. And by saying that, I'm not saying that this length cannot be 1 and this one cannot be 2. Because when I asked the question that does that mean L is equal to 1 and this equal to 2, I didn't say yes or no. I said not in general. By saying that, I'm saying yes, it can be true, but not necessarily. It can happen where maybe the length was 1 centimeter and this one was 2 centimeters. But there's a chance that if it's a ratio, that it cannot be that. That's what I meant. So I don't want you to arrest me someday and say that I said that if you have a ratio like B over what, it doesn't mean this is this, this is that. If your L was 1 centimeter and your breadth was 2 centimeters, then that was going to work. So the answer that I will expect when I'm asking you if this length is this and this is that, it will be not in general. By saying not in general or not necessarily, it means yes, it can be, but there's no guarantee. We don't know yet. Does that make sense?
Yes.
So this is what I want you to think about. Now we said that I'm coming back to this. When we're calculating the ratio of the length to that of the breadth, we said the length over the breadth is equal to 22 over 44. Does that make sense? If you look at this now, it will be 22, right? Let's say it's 1 times 22 over 2 times 22. So these two will cancel out and you're left with 1 over 2. Does it make sense?
Yes.
Do you understand it?
Yes.
Okay. So when you see it like this, when you see the ratio as given like this, I always think of it as this way. That there was something, there are 2 terms that cancelled out there, and it became the simplified version of this. As a result, when I'm writing it most of the time, as you will see when we're doing problems, it will be 1, maybe k over 2k. What is this k? K is whatever the value that was there that have cancelled themselves out. I will not bother myself by trying to think, because when you say 3 over 2, or maybe 3 over 4, when you say 3 over 4, a ratio of 3 over 4, you don't know what number was multiplying the 3 and multiplying the 4. You don't know those 2 numbers that have cancelled out. What you know is that, or maybe what is safe to think of is that whatever number that I had, those 2 were always cancelling out. So I can say that there's a cancelled out k and a cancelled out k at the bottom as well. And those k's will be 22 in this case. Does that make sense?
Yes.
In this case now, this was the length over breadth. Now let's go to the second one. We said breadth over height. So it was 44 over 88. As you can see, it's 1 times 44 and 2 times 88, 2 times 44 as well. These will cancel out and you're left with 1 over 2 as well. In this case, because these dimensions, which is your length and breadth, are not the same as these ones. So here you have combined length and breadth, and here you have combined breadth and height. So do we see the numbers that cancel out? You cancel the 22s then. Here you're cancelling what? The 44s. Are these equal? They're not equal because you have 22s there and you have whatever there. So which means if you're writing this ratio for the second, if now you want to represent this ratio as having these sort of numbers, you can't use the same letters above. Because now if I'm writing 1 over 2k and I'm saying this is exactly the same as that one. But it will be untrue to say that because the k is 22 here, but this is something else. So now in that case, it's safe to use a different letter. So which means I'll say this is, when I look at it this way, I'll say maybe this is 1 over 1a over 2a. So which means now this 44 now is represented by a here. So I would not want you to think that because the ratio was 1 over 2, so it's safe to use the k in both sides. So that's not what I'm trying to say. That's not what I'm trying to say. I'm not sure if that makes sense.
Yes, it does make sense.
It does make sense.
Yes.
Would you want me to talk more about these ratios?
Yes.
Okay. So now I'll say in this case, maybe this will be the last example. Let's say you have two ratios, R1, ratio 1 equal to ratio 2. Let's say your ratio 1 is equal to A over B, and your ratio 2 is equal to C over D. So, because these two are equal, it means this fraction is equal to this one. Do you agree?
Yes.
Yes, because R1 and R2 are equal.
Yes.
This is given, I've told you this.
Yes.
So, which means your A over B equals your C over D. So, my question is, you can see these are ratios.
Yes.
Your A over B is equal to C over D. Now, my question to you, does this mean this A is equal to C?
No.
Does it mean your B is equal to D?
No.
No. Because look here. Here, we had these two ratios equaling each other. But look at these fractions, they're not equal. So which means your 22 over 44 is equal to 44 over 48. But doesn't mean the tops are equal, doesn't mean the bottom are equal. What it means is that they just simplify to the same simplest ratio, or to the same simplest fraction. This is all I need you to know about this. And when I'm doing exercises or examples, real examples, I'll show you how to navigate these K's and A's and stuff. So for now, if you understand this, that is enough. I'm not sure if you understand it for now.
Yes, I do understand.
You do understand it?
Yes.
Okay, so I'm going to then clean the board, and then we're going to move to parallel lines, because this is all I need you to know about this. So you know parallel lines already, but I'm just going to do a bit of revision and add some few things. But this is all I need you to know, that just because two ratios are equal, it does not necessarily mean that the original fractions were also the same as well. Doesn't mean the numerators were the same, doesn't mean the denominators are the same. So in this case, this doesn't necessarily mean your A is equal to C and your B is equal to D. But what it means is that they just simplify to the same thing. So which means if you're writing your A over B, which means you can write it maybe as whatever and put a different letter as compared to the second one, because they might be different numbers. That's all I need you to understand at this point. So I'm going to clean the board. Then after cleaning the board, we're going to do parallel lines and then do some bit of revision, which we'll need for proportionality. Okay, so now we're going to discuss parallel lines. We did parallel lines already. If you start with our Euclid, when we studied Euclidean geometry, first explain parallel lines. So I want to do some revision and then talk about areas as well. So what are parallel lines? So parallel lines, as I've discussed them or defined them in the past, I vaguely define them as two lines that have the same orientation. I'm not sure if that makes sense.
Yes.
It's two lines that have the same orientation. What does that mean? It's either both of those lines maybe are horizontal, right?
Yes.
They're horizontal like this. Or these two lines are vertical. Can you see?
Yes.
So the orientation is the same. It's horizontal for both of them. And the orientation here is vertical for both of them. Also, they could be slanted, which is at an angle. They can be inclined, which is what you know your angle of inclination.
Yes.
So if they're inclined in the exact same way, which is they are exactly sitting in the exact same way, so we call these lines parallel. It's the lines that have the exact same orientation. So what do we know about these lines? These lines, we know that these lines never meet. Because if they have the exact same orientation, it's either they're both moving away from each other. They're always moving. So either they're sitting in the exact same way or moving away from each other the entire time. I'm not sure if that makes sense.
Yes.
Because if they are both horizontal, the distance between them will always be the same because they're horizontal. They're sitting in the exact same way at a fixed or at the same distance apart. I'm not sure if you understand that.
Yes, I understand.
So these two lines are horizontal. So they're always like this the entire time. So the distance between them will always be the same. So which means if you take the distance between any 2 points, it will always be the same distance. So, and you know the distance between two lines is always the perpendicular distance, right?
Yes.
So even here, the distance, which is this D1 here and the D2 are the same. Because the distance between parallel lines is always the same. Because they're always moving away from each other. Or maybe at fixed points, I don't know. So in that case, of course, this is 90 degrees and this is 90 degrees. So I'm just saying that the distance between two lines is the perpendicular distance. I'm not sure if you understand that. So if you're trying to find the distance between the two lines, you can't find the distance between this point and that point and say that's the distance. It should always be the one that is perpendicular to both of them. In the same way, if you're looking at distance here, so let's say this is D3, right? You can see this should be perpendicular distance between them. So these two distances, D3 and D4, they should be the same. So even here, so which is I think it would be like this. It can't be vertical like this one. So the distance between these two lines should be something along like this. Here's 90 degrees, should be here's 90 degrees. So in this case, this is maybe D5 and D6. So in this case, for example, I will say parallel lines are two lines that have the exact same orientation. They never meet and they are always the same distance apart. So in this case, your D1 equals D2. And in that case, your D3 equals D4. And in this case, your D5 equals D6. Any questions about this?
No questions.
You remember parallel lines?
Yes.
Now, we spoke about triangles as well. We spoke about triangles previously when we started Euclidean geometry. I spoke about different types of triangles like isosceles and all that kind of stuff. But when I was defining those triangles, I also spoke about angle classified triangles. So the angle classified triangles are triangles that are named, maybe you'll name it based on its angle or the amount of angles that you have. For example, your right angle triangle, because it's named based on the angle, right? So it's right angled. And maybe your acute triangle and your obtuse triangle. Do you remember those? I want us to speak about those because when I did mention them, but I never spoke much about them. So the reason I'm bringing them back right now, I want to remind you of them and then also speak about the way of calculating the area of those triangles. So in this case, let's speak about these triangles. So I will first start with, I'll say triangles, which is we're interested in areas, to be honest, areas of triangles. So let's say we have this triangle over here. It says A, B, C. And let's say this angle is 90 degrees. Can you see this triangle?
Yes.
What kind of triangle is this one?
Right angle triangle.
This is a right triangle. Right angled triangle. Okay? Right angled triangle. So, do you know how to calculate an area of a triangle?
Yes.
It's half base times perpendicular height. So if you want to find the area of a triangle, it will be half base times the perpendicular height. What is the base? It's whatever that your triangle is sitting with, right?
Yes.
Times the height that will be perpendicular to that.
Yes.
But that's not the only way of calculating a triangle. It does not necessarily have to be what it is sitting with. You can think of a base as the side that you are interested in using. I'm not sure if you understand what I'm trying to say.
Yes.
As long as you take that side, you can use any of the sides, even if it's not sitting with that side. You take that side and multiply and use and find its the height that would be perpendicular to that. Do you understand?
Yes.
For example, here, if you're looking here, What would be the logical answer for your base? Which one would you say is your base here?
BC.
It's easy to say it's BC because it's sitting with BC. Because that's what you know as the base. The base is whatever that your triangle is sitting with.
Yes.
But someone else might want to look at
AB.
AB as a base.
Yes.
Now, the only thing that will matter is the perpendicular height, which is whatever height that will be perpendicular to that. Or maybe others will call it an altitude. The perpendicular height is sometimes called an altitude.
Okay.
Because some people get confused when you say perpendicular height, but your height is horizontal. Like, which one is this one now?
Okay.
So the proper word that is neutral is altitude. Are you with me?
Yes.
Okay. So in that case, if we want to find the area here, let's try to find the area of this triangle. So I'll say area of triangle ABC. So it's half base, right?
Yes.
It's going to be half of your base. What is your base? You say your base is BC, right?
Yes.
Sitting with BC times the perpendicular height. What is the perpendicular height?
AB.
Is this one here, because here is BC. So if you're calculating, it will be half of whatever side that you choose times the height that will be perpendicular to it,
Yes.
times the altitude.
Yes.
So your altitude or your perpendicular height is AB. Are you happy with this?
Yes.
Now let's say we use this one first. Now let's use this one as our base.
Okay.
So in this case, also okay. Number 2, our area of triangle ABC. It's the same triangle, right?
Yes.
It's going to be half base. Our base is what now?
AB.
It's AB. Now, which side is perpendicular to AB?
BC.
It's BC.
Yes.
So it is BC. And if you look at this, and that is exactly the same thing. But the order is different because look at BC, there's BC, there's AB, there's AB. So it's the same thing. I'm not sure if that makes sense. Does it make sense?
Yes, it does make sense.
So,
It does make sense, but I didn't know if it is the same thing.
yeah, because if you're calculating the area of this triangle, the area of this triangle, if you want to think about it in a simple way, is the amount of space that is covered by that triangle.
Yes.
It's the amount of flat space covered by that triangle. So it doesn't matter if you're sitting this side or sitting here or there. The amount of flat surface that will be covered by this area is going to be the
So
same.
it will come out the same.
So the area should come out the same.
Okay.
So the order in which you multiply these things doesn't really matter.
Okay.
So multiplication in real numbers is commutative,
Okay.
which is the order is not important. In a similar way, you can say, okay, well, how about to calculate? This was the second one. How about to calculate from here?
Okay.
Okay. So in this case, here's what you need to pay attention to. You said this is the half base, right?
Yes.
Times perpendicular height.
Yeah.
Times half this base times perpendicular height. For the second one, you say half this base times this perpendicular height. What you need to understand, what is common in both of these perpendicular heights of yours, they start from your base and go to the third vertex of that triangle.
Yes.
Because you said this is your base, right?
Yes.
This is your base. This is your base. Perpendicular height starts from this base of yours to the third vertex.
Yes.
And you said this is your base, and your perpendicular height starts from this base of yours to the third vertex.
Yes.
So if you're calculating the area of this triangle, it will be your base, which will be your AC. Now your perpendicular height should be starting from somewhere to the third vertex. I'm not sure if that makes sense.
Yes.
So your perpendicular height, it will be a line perpendicular from the third vertex. So, which in that case, we can say maybe this is D, maybe, I don't know, where the perpendicular is found on that line. So in that case, to calculate the area of triangle ABC, to be your half base, which is your what?
AC.
AC, times perpendicular height, which is what? Which is BD. All this area should come out the same. This is an area for an acute triangle, for a right angled triangle. Now let's move to an acute one. It will be nice, this one. So let's go to an acute triangle. acute area. So in acute triangle, it's a triangle like this one. All of the angles are acute angles. Let's say it's x, y, and z. All of these angles are acute and they're all less than 90 but greater than 0. Right?
Yes.
Less than 90, greater than 0. Less than 90, greater than 0. Less than 90, greater than 0. So it's an acute triangle. So if you're looking at this, it would be easier to say, okay, the base, what is the common base here? Or the easiest, it would be yz, the nicest one.
Yes.
So, but to find the perpendicular height, you know, should start from yz to the next third vertex.
Yes.
So which means the perpendicular height, if you look at yz at the base, it should be something like this. Not sure if that makes sense.
Yes.
So if we want the area, we're going to say, okay, this is area number 1, right? So we'll say 1 area of triangle x, y, z, equal to half base, which is what? Yz, times the perpendicular height, which is what? Maybe let's say this is what? W, no, let's say P, right? That is P. So to be half base, which is this, times the perpendicular height, which is perpendicular height or altitude, because perpendicular height is the altitude, right? Yz times xp. Are you happy with that?
Yes.
Now let's go to the second part. Let's use this side now. We can use yz or xz. We can use xz as our base. Do we have an altitude?
No.
So an altitude from there will be starting from here to there. So we should always start from your base
Okay.
to the other vertex.
Okay.
That's what the same thing that I said here.
Yes.
Because look, we said this is the base. The altitude started from this base and to the third vertex. We said this was the base. The altitude from this base to the third vertex. We said this is the base from this base to the third vertex. It's the same principle. So here is your 90 degrees over there. This is, we said that was P. Maybe let's say this is Q. Right?
Yes.
So if you want the area of this triangle for the second way, so okay, our area of triangle x, y, z is equal to half base. What is your base there?
XY.
Xy times altitude, which is what?
ZQ.
ZQ. Or QZ. Clear?
Yes.
No problem. That way. So these areas should come out the same. Because you're calculating the amount of flat space that will be covered by that triangle. So if those dimensions are correct, then they should cover the same space. So in that case, let's say we use the third side. Here's the third side over here. Then, and then, here's the 90 degrees here. PQ, let's say that is R. Here. So, what is the area for the triangle? Area of triangle XYZ. What is the area? It's going to be half of what?
XZ
XZ
times YR.
times YR. That's it. So those areas are all equivalent. Because you're calculating the same amount of flat space covered by the triangle. Now we're going to the last one that I'm going to cover. An obtuse triangle. Like here, this was an acute triangle. All of those angles were acute angles. Now, I'm sure you're asking yourself, does it mean for an obtuse triangle, all of the angles are more than 90 degrees? No, that's not the case. If there's one that is more than 90 degrees, that's an obtuse triangle. So, how do they look like? This can be obtuse. These are areas that I'm going to calculate here. So, obtuse triangle, they look like this. Not sure if this is clear. So you can see that I think we can both agree that this is more than 90 degrees.
Yes.
So this is let's say this is P, Q, and maybe R here. Are you with me?
Yes.
This is an obtuse triangle. So on this obtuse triangle, I'm not going to go very, very hard on it, but I can if needs be. But I don't think there's need for me to go very, very hard. So if you're looking at it, you wanted to calculate the area. Which side would you say is your base here?
That's QR.
It's QR. So here's QR. QR is an easier base to identify.
Yes.
So let me write it as 1. So if you want the area of triangle PQR, it will be half base times perpendicular height, right?
Yes.
The problem is that I said that if this is your base, I said your perpendicular height should start on your base to the other vertex.
Yes.
But now, if this is your base here, and this goes from here to there, yeah, it goes from the base to the vertex, but it's not perpendicular.
Yes.
Are you following me?
Yes.
So you need the perpendicular height, which means what you need essentially is the height to your vertex. I'm not sure if you're following me.
Yes.
You need a height to your vertex. So to do that, this is how to think of this. Think, because you want to have a height from the base to the vertex. Your base is short, it ends here, right? So what you need to do, just think of your base as an imaginary extension of it. You're not extending it, but you're just sort of extending it so that you can see where the perpendicular height is. So are you following me?
Yes.
So now, the height from there now to this base is your perpendicular height here. I'm not sure if you get this.
Yes.
So this is your perpendicular height, H1 maybe. So if you want the area now, it will be half this base times the perpendicular height, which is that one over there.
Yes.
So that is the vertical height or the perpendicular height from your vertex to where your base line is.
Okay.
I'm not sure if this does make sense.
It does.
So if you want the area of this, it will be half base, which is what QR, times the perpendicular height, which is H1 over there. So I'm not going to do other sides because it will be similar to the previous ones. But I wanted to show this at least. Because if you use this as a base, you have to find the perpendicular height from here to there. I'm not sure if you get what I'm trying to say.
Yes.
It's that sort of thing. So this is how you calculate it. This height is the height from the top to this line over here. That's how you find the area of this triangle. Does it make sense?
Yes.
Okay. So another thing that I want to talk about, I want to talk about areas. I want to talk about areas between parallel lines. Right? I'm going to talk about areas between parallel lines. I hope this does make sense. Does it? Do you understand it?
Yes, I understand.
Let's say you have two parallel lines, this line here and this line over here. Let's say these two lines are parallel. Right?
Yes.
Let's say between you have these vertices here and they form this triangle. Can you see them?
Yes.
So this is A, B, C. Can you see it?
Yes.
And let's say maybe this goes to this side as well. Does it make sense?
Yes.
So let's say you were to calculate, or let's say this is D. So let's say you wanted to calculate the area of triangle, A, B, C, which is A, B, C. Can you see it?
Yes.
Or maybe, you know what? Let me use different colors for this so that it can be very clear. It doesn't look very clear to me right now because I have different colors so that I can use. So let me try them. Okay. I have this line and I have this line. So let's say these two lines are parallel, right?
Yes.
So you have, let's say you have this point here and this point here. Can you see?
Yes.
Okay. The other one is purple. So the red triangle, let's say it's A, B, C. And the purple triangle, it's C, B, D. Not sure if that makes sense.
Yes.
You know how to calculate the area of a triangle. If you look at the red triangle, what kind of triangle is that based on this angle-based triangles?
Right angle.
Hmm?
No.
The red triangle.
No. I think it's obtuse.
Yes, it is an obtuse.
Yes.
And the purple one?
Obtuse.
Yeah, both of them. These are obtuse triangles. They look like this one.
Yes.
Do you agree?
Yes.
Okay. So in that case, if you were, would you agree with me when I say both of these triangles ABC and BCD, they share a base, a common base?
Yes.
What is that base that they share?
BC.
They share a common base because both of them are sitting with BC.
Yes.
So they have a common base. So if we were to calculate the area of triangle ABC, let's say now, we're calculating the area of triangle ABC, which is the red triangle. It's going to be half base. What is your base?
It's BC.
Is BC times the perpendicular height. The perpendicular height is this height from here down here. Because an obtuse triangle, same as this one.
Yes.
You're looking at an obtuse triangle.
Yes.
So the perpendicular height will be this height over here. Same as that one. So let's mark it down and call it H1. This is the perpendicular height. This, if you look at the red triangle, this is the same situation as this one.
Yes.
So this is maybe H1 over here. And in that case, it will be half base BC times H1. Times H1. Do you agree?
Yes.
So help me calculate the area of triangle CBD. So area of triangle CBD. What is the area of triangle CBD?
It's half.
Half BC, because it's also at this base, half BC
Times H1.
H1 is this side. Let's say H2. Let's draw H2 on the other side. I'm not saying you're wrong, but let's just say H2. H2 over here. So I'm going to push H2 over here. But you said H1. Why did you say H1?
Because it's the same distance.
Yes. Because these two lines are parallel. The perpendicular height, like this perpendicular height here, will be the same as that one.
Yes.
So it was going to be the same if you had said H1.
Yes.
So these two triangles, this triangle and this triangle, they have exactly the same area. Because they have the same base BC and the same perpendicular height, which is the distance between two parallel lines. So those areas, those two triangles, have the same area. Not sure if that makes sense. In that case, if it does make sense, I think now you are ready to do the proportionality theorem. Because all what we've done, it was preparing us to do that. So I'm going to clean that because as long as you can see that this distance and that distance are exactly the same, then we're done. So these two triangles, they have exactly the same area. So I'm going to clean the board and then we do the basic proportionality theorem. Okay, so now that we're done revising the areas and all other stuff and ratios, now we're ready to do the proportionality theorem, which you're expected now to understand for your grade 12 exams. So the basic proportionality theorem states that if a line is drawn parallel to one side of a triangle, right, then that line divides the other two sides proportionally. A line drawn parallel to one side of a triangle divides the other two sides proportionally. What does this mean? That means if you have a triangle, I'm going to call the triangle ABC, right?
Yes.
If this triangle ABC is drawn, here's a triangle. That's like if you draw a line that is parallel to one side of a triangle, then it will divide the other two sides proportionally. So in this case, what do? We draw a line that will be parallel to one side of the triangle. So, and it's going to divide the other two sides proportionally, which means the line that you're going to draw, you're going to somehow maybe join some two other lines. Do you understand?
Yes.
The line that you're going to draw that will be parallel, you should be joining some two other lines somewhere. In this case, what I'm going to do in this case specifically, I'm going to say, okay, this line of ours, it should join these two sides. Let's say this line is parallel to this one. And let's call this point D and point E over there. So what they say, if you have a triangle, if you have a line that is drawn parallel to one side of the triangle, it will divide these two sides proportionally. What does it mean, divide the other two sides proportionally? When I was doing ratios, I did define proportional. And I said proportional means at equal ratios. Proportional means same ratios.
Yes.
When you're saying proportionally, it means this line of yours AD will divide these two sides at same ratios, at equal proportion, at same proportions. I'm not sure if that makes sense.
Yes.
When I say at same ratios and say equal proportions, it's the same thing, even if I'm saying proportionally. Does it make sense?
Yes.
In that case, what does it mean? It means that if you take the ratio of the same parts, those ratios will always be equal. I'm not sure if you understand what I'm trying to say.
Yes.
Because if you say the top AD and divide by the bottom part, it should be equal to the corresponding ratio of the other side. So it should be AE over EC. I'm not sure if you get that.
Yes.
So what this means essentially, if you have this condition, this divides to other sides proportional. It means your AD means your AD over your DB equals what? AE over EC. So which means if you take the ratio of the same parts, they will be equal. If you have a line drawn parallel to one side of a triangle, it will divide the other two sides proportionally, which means it will divide those two other sides at equal proportions, at equal ratios. These are the ratios, which is, this is not the only ratio that works. As long as you take the ratio of the same parts. You can say you can say AB over AD. You said the entire thing divided by the top should be equal to the entire thing AC over AE. As long as you take the ratio of the same parts. I'm going to get to that part, other ratios later. But for now, I'm only going to stick to the basic one. The one that will allow us to go and fish for more other outcomes.
Yes.
So in this case, this is what we want to prove. Because the part, a line drawn parallel to one side of a triangle, that's your given information. That is some sort of given information.
Yes.
Then this is what we want to prove. Divide the other two sides proportionally. If this statement was written as if and then, you're going to say if a line is drawn parallel to one side of a triangle, then it divides the other two sides proportionally. So this part is the part that we want to prove. Now, we want to prove this. How do we prove this? So we first we are going to use areas to prove this for simple. We're going to use areas. We know how to calculate. We just reminded ourselves on how to calculate areas.
Yes.
So how are we going to do that? We're going to say, okay, we need some constructions, right? We need some construction. Let's construct some stuff. Construction. Are you with me? So what I want us to construct first, I want us to have two altitudes in this triangle. You see this small triangle ADE, in this small triangle, I want us to have altitudes, which is your perpendicular heights. One perpendicular height will be coming from here, and the other one coming from there. The one that comes from the vertex, with the top vertex, we don't care about. I'm not sure if you understand what I'm trying to say. We need perpendicular heights that we will use to calculate areas of that small triangle. So in that case, We can just draw. Let's just draw our perpendicular height here. Can you see?
Yes.
Let's say this point is x here. Here's our perpendicular height. And we draw another one from here to that side there. That side is y. Are you happy with that?
Yes.
After drawing those, let's go and write them on the construction. And say, on our construction, we're going to mark x and what? And y. On what? On AD and AE, respectively. So that EX and dy are perpendicular heights. Perpendicular heights in triangle ADE. I'm not sure if that makes sense.
Yes.
Does it make sense?
Yes, it does.
What I did, I marked X and Y on AD and AE respectively. What does this mean? It means I'm marke u-X no Y, ku-AD no AE ngokulandelanayo.
Yes.
Which means u-X uku-AD, u-Y uku-AE. Now X AD, Y AE. That's what that respectively means. It means you marked your X and your Y ku-AD no AE ngokulinganayo. Hence umntu amazi uba enyiphi. So that your EX and your DY are altitude. So the EX no DY is perpendicular heights in the triangle. Which is triangle? In triangle, maybe. In triangle ADE. I'm not sure if that makes sense.
Yes.
Does it?
Yes.
Then, what else? Another construction that you will make. You made this, right?
Yes.
You then just going to join these diagonals. You join DC
And EP.
and EB. Just mark these. So what we're going to do, okay, what we'll do next, we're going to join what?
DC.
DC and
BE.
BE. That's the only construction that you do. Then from there, you just calculate areas. Are you following me?
Yes.
Now we're going to start with the proof now. We're going to calculate the areas. But now with the areas, you need to be strategic. You want to AD over DB, EC, AE. Do you see this? Now, when you're calculating these areas, you want to make sure that these things that you see here, they appear on those areas. You look for the triangles that will contain these things. So you will calculate 4 areas, 4 of them. Do you see an area do you see a triangle that contains AD?
AD.
Yes.
Yes.
Yes. You look at ADE, the small triangle. It contains AD. Because you have AD there, start with that area that contains AD. Okay. So what are we going to do? So, okay. In triangle, what? ADE. We are going to AD because we see AD.
Yes.
Go and calculate the area of the triangle using AD that you went there because of. So, if you want your area of triangle ADE, what will be that area?
Area of triangle
DE.
ADE.
Yes.
Okay.
And you want your AD to be your base or to appear. So if you want your AD to appear on your area formula or area whatever, you must use your AD as well.
Yes.
So you can use your AD as a base because you do have a perpendicular height to AD.
Yes.
So what will be your area?
So it's half base.
Half base. What is your base?
It's AD.
AD times what?
Perpendicular height.
What is your perpendicular height?
It's EX.
It's EX. There's your area for AD. We're done with it. So we're done with this part. Do you see that?
Yes.
After doing that, you go to the next part. What is the next part?
It's dB.
It's dB. Do you see anything with dB? Do you see any triangle that contains dB?
Yes.
What is it?
Any triangle?
That contains dB.
Yes.
What is it?
It's triangle DBE.
dBE. This triangle. Now, go and calculate the area of that triangle. And you're using your dB as your base as well. What kind of triangle is dBE?
It's obtuse.
It's an obtuse triangle. There is perpendicular height over there. Does it make sense?
Yes.
It's an obtuse triangle.
Yes.
Here is it over here. And this perpendicular height, you have to extend this part so that it goes up there. So what is your area? So we're going area of triangle DBE right now, because we're done with this one. So we're going to the second one. What is area of triangle DBE? What is it?
It's half
Half base. What is what?
BD.
DB. Let's say DB because we want to be consistent.
Okay, DB.
DB times perpendicular height,
Perpendicular height in EX.
which is EX. I'm not sure if you see this.
Yes.
Can you see it?
Yes.
So you're done with that part and you're done with that part. Do you see that these two things are dividing each other?
Yes.
Divide these areas.
Okay.
So take the area of the top one, where your AD is at the top, and divide it with the bottom one. So let's do that and say the area of triangle ADE over area of triangle DBE. Is it? DBE is equal to what? 1 over 2 of AD times what? EX over 1 over 2 times DB times EX. So this and this go away. Do you agree?
Yes.
This and this go away. Do you agree?
Yes.
What are we left with? We're left with AD over
BD.
DB. Do you see that this is this?
Yes.
We're done with that part now. So we found that we found something with this. We're going to do the same thing for this part. And then once we do them, we're going to try to prove that the ratios are going to be equal. I'm not sure if that makes sense. Okay. In that case, you go to try to find a triangle that contains AE. Do you see any triangle that contains AE?
Yes.
What is it?
It's triangle ADE.
Look at triangle AD again. So you're going to calculate the area of triangle ADE, but now using the other side. So, say the area of triangle ADE equals what? Half of what?
Of AE.
AE times what?
Times YD.
dy. Fine. We're done with this part. Is there any triangle that contains Eastern Cape?
EC.
EC.
Yes.
Uh-huh.
It's triangle
Uh-huh.
BEC.
Try what? Okay.
EC.
Yes, I can see it. EC, yeah, it said BEC, but
We can
but-
use UDEC.
DEC, yeah, we're going to use this one.
Yes.
DEC. So area of triangle DEC, December. It's going to be half of what?
Okay, DEC, right?
Mm-hmm.
Okay, so it's half EC
Half EC times the perpendicular height. What is the perpendicular height of that obtuse triangle?
perpendicular height.
Yeah, if you say it's triangle DEC, you can see this triangle over here. DEC, right? Where is this perpendicular height?
It's perpendicular height.
This is an obtuse triangle.
Yes, so perpendicular height is dy.
It's dy. So it's going to be half the space time obtuse triangle, which is dy.
Yes.
dy. Once you are here, you divide, take a ratio of these triangles. So what do you say? So area of triangle DADE, right?
Yes.
Over area of triangle DEC is equal to half AE times dy over half
EC
EC
and
dy. So this and this go away, this and this go away. We're left with AE over EC.
EC.
The goal was to prove that this and this are equal. That was the goal. That's what we're trying to do.
Yes.
What we have done so far is we have found that the area of triangle ADE over the area of triangle DBE is equal to AD over DB. Do you agree?
Yes.
And we found that the area of triangle ADE over the area of triangle DEC is equal to AE over EC. The only thing that we'll have to do now is to show that these two things are equal.
Okay.
So how are we going to do this? Would you agree with me when I say the area of ADE is equal to the area of ADE?
Yes.
The area of ADE is equal to the area of ADE.
Yes.
Because the same triangle.
Yes.
Do you want me to write that down?
No.
No. If you can show that the area of the bottom one is the same as this one, then this will be equal to that.
Yes.
Because the tops will know exactly they're the same.
Yes.
If you can show that the bottoms are the same, then this part will be equal to this part. So will these two parts.
Yes.
So let's go and look at these two triangles. This triangle ADE, it's triangle DBE and DEC. Let's suppose that I use a different color. Let me try to find a green color. So I'm going to change the color of this one. I'm going to make it green. Can you see the green triangle?
Yes.
Triangle DBE is green now. And look at triangle DEC. DEC is going to be red. Can you see it?
Yes.
Can you see?
Yes.
Look at these two triangles. These two, the red and green one. What do they have in common?
Triangle BDE
And DEC, what do they have in common?
and DEC. Okay, wait. You said triangle?
The green one, DBE and DEC. These two triangles. This one, the green one, and the red one. What do they have in common?
Yes.
They have the same base. They're sharing DE.
Yes.
And you know together the area of a triangle is half base times perpendicular height. So if you're looking at the green one, this perpendicular height will be somewhere here. Do you agree?
Yes.
And if you look at the red one, its perpendicular height will be somewhere here. Do you agree?
Yeah.
And these heights are equal.
Yes.
Because these are heights between two parallel lines.
Yes.
So the area of the green one and the red one should be the same.
Yes.
Because they share the same base and they have the same perpendicular height.
Yes.
So which means if you say half base and perpendicular height for the red and green, they are going to come out the same.
Yes.
That's the end of the proportionality theorem. I'm not sure if you understand what I'm trying to say. What I'm trying to say is the green one have the base DE and the perpendicular height, which is the distance between parallel lines. And the red one have the same base DE and the perpendicular height between the parallel lines. So if you're trying to calculate the area of this triangle, it's going to be half base and perpendicular height. The bases are the same and the heights are equal as well. So the areas of these two triangles are equal. So what we can say is the top area and the top area are exactly identical. So the bottom one, if you can show, which you just explained, that they are the same, which is this ratio and this ratio are exactly the same, and so are the right hand sides. So in that case, we're going to say, okay, the area of triangle ADE, of DBE, because there's no need for us to explain this, is equal to the area of triangle DEC. The area of this bottom triangle is equal to this one.
Yes.
Why? Because they have the same base. They have the same base. What is that base over there?
It's DE.
It's DE. And they have the same perpendicular height. The same perpendicular height. Do you understand?
Yes.
And you have to explain this perpendicular height. And say, okay, is the distance between parallel lines. Why? Because your DE is parallel to BC. Not sure if that makes sense. Or maybe let's say height between parallel lines, because your DE is parallel to this. So these two things are equal. So what does this mean? It means your area of triangle ADE over the area of triangle DBE is equal to the area of triangle ADE over the area of triangle DEC. Do you understand?
Yes.
Because this and this is the same thing.
Yes.
This and this will just explain that they are the same. So which is this, which was AD over DB, is equal to this, which is what? AE over EC. We're done here. I'm not sure if that does make sense.
Yes.
Does it make sense?
Yes.
Any questions for me?
No questions.
Now, what I want to talk about next. What I want to talk about next is an extension of this, right? So here we set a line drawn parallel to one side of the triangle, divided the two other sides proportionally. That's what we said. So I want to talk about a few other things now. So when I draw the line that is parallel to the third side, I draw it inside this triangle, right? I'm not sure if you get that.
Yes.
I drew it inside this triangle. Let's suppose this triangle looked like this. ABC. Because the original triangle was ABC. Let's say we had A, B, and C. So the way I drew this line DE, I drew it inside here. What if this line maybe was continuing after this? I'm not sure if you get that.
Yes.
And we drew this line, maybe this parallel lines, to intersect the other. Because here we clearly drew a triangle and then we divided it by this parallel line. So here, let's say that it was continuing, and on that, let's say that this line, the line AB and AC were extended, so that they intersect a line that will be parallel to this. I'm not sure if you get what I'm trying to say. The same ratios will apply.
Yes.
I'm not sure if you get that.
Yes.
The exact same ratios will apply. So, because this is your D, so your D will be sitting here. Your D will be sitting here, and your E will be sitting there. Because you can see that it's clearly an identical image, or close to identical. Because the way I drew the parallel line, I drew it inside, in between these. But what if it was under? Let's say maybe your triangle was extended so that it intersects some line that will be parallel to the third side. These ratios will apply, which is, you can see now, it's the entire side. Yeah? Over what? Over DB, which over the lower part. Because it's AD over DB. So it's the entire side over the lower part. And then on the other side is AE over EC, which is the entire side AE over EC, which is the small part over there. Which proves what I was saying to you earlier, that this is not the only ratio that holds. As long as you take the ratios of the same parts. Because here it was top over bottom, top over the bottom. Even the bottom over the top, bottom over the top, it works. I'm not sure if you understand what I'm trying to say. So this one clearly shows that you can say the entire side over the lower part is called the entire side of the lower part, which is what we were given. But on the original drawing that I had, I didn't give it. It was not showing the entire side and the bottom. It was showing the top and bottom. But on the second diagram, I'm saying the entire side over the bottom, entire side over the bottom. As long as you take the ratio of the corresponding sides, it works. So the other one that doesn't look very familiar. You see what I did? The normal triangle ABC, which is your normal ABC, I extended it down. What if it was extended the other way? I'm not sure if you understand what I'm trying to say.
Yes.
So I'm going to have your ABC like this. So here's your A, here's your B, and here's your C. So on the first diagram, the one that I used for your proof, what did I do? I had my ABC and then put the parallel line in here. On the second one, I said, okay, I have my ABC. Let's suppose these were continuing. And then now, the parallel line intersect the continuation lines. I said this thing will also hold.
Yes.
Do you understand?
Yes.
Now, I'm saying, okay, I have my ABC. Now, I want now the continuation of these two not to be down, further down. I want it to be further up. So in this case, this E of yours will continue going up,
yes,
and D will be on the other side.
Yes.
So in that case, you have something similar to this. And this is parallel to this. So you have your triangle ABC, and maybe its extensions intersect a line that is parallel to the third side. Right?
Yes.
So what you have here, it will be your D, because you can see your D is there, so it will continue that way. So this is E over here. The same proportions work. Which means if you say your AD, here's your AD over DB. Where is DB? Oh, sorry, it's AD over the entire side DB. Can you see that?
Yes.
It's AD over the entire side. This will be AE over the entire side. I'm not sure if you understand what I'm trying to say. Do you understand?
Yes.
Because look, so this triangle is this one is the big one here, and this one is the small one, that AD over there. I'm not sure if you're following me.
Yes.
So in that case, this and this, they preserve the proportionality theorem as well. They preserve those proportions. And what you need to keep in mind is that this is the same side, all of it. This is one side, this, B to D. And this is one side, this. So in that case, if you say, okay, my AD, if you say AD corresponds to this, you can say AD over maybe AB, right? So in that case, it would be your AE over your AC. These as ngendawo ezimbili. The same way as ngendawo, yes.
Yes.
The same way as ngendawo, yes. But here it's easier to see that this and this are on the same line. 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 This is not. This and this are on the same line. This and this are on the same line. I'm not sure if that does make sense.
Yes.
And you can prove the proportionality theorem using these diagrams. How? If you can use the same construction. Let's say use the same construction as this. This construction up to there is the same. It will give you the same proof. Look, you mark your X and Y on AD and AB. Where's AD? You mark your AD and AE. You mark AD and AE. Or you mark your X on AD, right? Let's say, where's AD? AD is here. You mark your Y on AE. Here's your Y over here. Not sure if that makes sense. What else do you do? You join altitudes. Here they are. Do you see that?
Yes.
What else do you do after that? You join DC and BE. Here's your BE here. Here's your DC over there. Isn't that what you did? Okay. Now you want to calculate the area of ADE. Let's look at ADE. And what involve AD, right? Look, AD. Here's AD. So it's going to be half AD times perpendicular height, which is what?
Which is AX.
Look at that.
Oh.
Now, what else do we do? We went on to calculate the area of DBE. Where is DBE? Is DBE is this big triangle over here.
Yes.
Here's the altitude of DBE. Can you see DBE is this one?
Yes.
Here's the altitude of DBE. So it's going to be half base, which is DB, times perpendicular height, which is what?
BX.
Look at that. So you can follow the same construction here, and the same proof works. Same construction here, the same proof, same thing. I'm not going to do all of them, but you can see the point.
Yes.
Because you can, if you can use this diagram, it will be an exercise. You can use this diagram with the same constructions. It's the same thing. So this and that, they all present the proportionality theorem, the basic proportionality theorem. And I'm done with this proof now. Does it make sense?
Yes, it does make sense.
So what I'm going to do, I'm going to clean the board, and I'm going to talk about more properties. And then I can do the converse as well, but there's no need, but I can do it and then do the outcomes, and then it'll be done. So the last part, I just want to, the last thing that what I want to do after this is to show all the ratios that work, so that you don't think the only ratios that work is this over this. You know that as long as you take the ratios of any corresponding parts, they will work. So I'm going to clean the board, and we're going to do that. Okay, so now we're going to just continue with a few properties or ratios that are going to hold for the proportionality theorem, so that everyone knows them. Okay? So the one that we proved was that 1 AD over DB is equal to AE over AB. Do you agree with that?
Yes.
Are you happy with that? Even the opposite holds, right? Even the opposite holds, which is, if you say, you said ADB, you said AD over DB is equal to AE over this. Even if you say this over this, which is your DB over AD equals to EB over AE. This holds. I'm not sure if you understand. I'm not going to write all of them. The other one, you can say this over this is equal to this over this. Or this over this is equal to this over this. This over this is equal to this over that. As long as you take the ratio of the same parts, it's going to work. Does it make sense? Do you understand? The other one, number 2. Let's say on this AD over DB, you know, must is equal to AE over EB. It's this one. How about we add 1 both sides? When you add 1 both sides, we can simplify this. This is over 1, right? This is over 1. So we can say it's going to be this times this all over DB. Do you agree? This time that's AD plus DB. Do you understand? Yeah? Could you just add the fractions?
Okay.
Is equal to same thing. This time this all over AB, right? This time this is AE plus EB. I'm not sure if this makes sense, because it's this one. I just added 1 to both sides. So if we do this, look, you have AD plus DB. Go to the diagram and look at AD plus DB. What is that?
D
plus
DB.
It's the entire side, because AD and DB. So it's all of AB. So it's going to be AB over DB is equal to, what is the answer to this? AE plus EB.
A.
Is AE plus EB. Oh.
C.
How did you get? Something's wrong. This was supposed to be EC.
C.
Supposed to be C here. Where is it? EC. C here. Is there anything that we messed up? Yeah. I think we're good now. Yeah, it should be
And the EC.
C here. EC. This is supposed to be EC. Everyone happy now? So it's AE, right?
Yes.
Plus EC. So AE plus EC is called, so
Okay.
AE plus EC is called AC. It's all of AC. So this is called AC over EC. So if you look at this one, it was involving the top and the bottom. So the top ratios and the bottom ratios. Because you look at AD is the top and your DB is the bottom. AE and this is top and bottom. If you look at this now, is the total side, which is AC or AB, and what? And the bottom. So my point is, it can be the ratio of the top and bottom, or the ratio of the entire side and the bottom. If this works, even the opposite will work. Which is the opposite will be what? It will be DB over AB. Do you agree?
Yes.
Is equal to EC over AC. So now it also involves the total and the bottom. The last one that I'm going to do. So I'm going to take this one, which is the DB over your AB, equal to EC over your AC. I'm going to subtract 1 and subtract 1. Yeah? So what we have, we'll have this over 1, this is over 1. This time this is AB, cross multiply. This time that is DB minus AB, which is equal to EC minus AC all over AC. I'm not sure if that makes sense. Now I'll go to this now. Let's go to the diagram now. And say DB minus AB. Where's DB? DB is this entire side, is this bottom. On that bottom, you are subtracting the entire side AB. So you're saying DB minus AB. Do you agree with me when I say you're going to be left with a negative AD?
If we're saying DB
DB minus AB.
minus AB.
Yes, because
yes.
it's DB with this part minus the entire thing. This will go away and you'll be left with a negative of that.
Yes.
Because it's big, it's AB is bigger.
Yes.
So you're left with negative AD here. So it's negative AD over AB equals what? Negative AD over AB equals, what is EC minus AC?
You see,
EC, which is this part,
that's going
minus
to be
AC. Minus AE over AC. Do you agree? So we can divide by negative both sides, and this is an outcome. This is a third outcome.
Okay.
Which is, even its opposite will work as well. So if you say AB over AD equals to AE over AC. So these are the ones that I think are the most important in my opinion. Because if you look at this, what is AB? AB is the entire side, it's the total side. And this one is the what? AD is the top side. So you can see that if you can take the ratio of the top and the bottom, as long as it's the corresponding parts, as long as the same parts, you can take the total and the bottoms, we're taking the total and the top. So what we're left with now is we're left with the converse of the proportionality theorem. So I'm not going to do it here, I'm tired. So we're going to do the converse, and its proof, and we're going to do the outcomes of the proportionality theorem, and then do the examples on the next video. I'm tired now, and I hope this does make sense to you, as it does to me. Does it make sense?
Yes, it makes sense.
Yeah, so I'm going to do the converse on the second video, together with other outcomes, and then we're going to do examples as well, so that we know how to apply the proportionality theorem. And we're done for the day. Thank you for watching. Cheers.
Cheers.